Hi again. So in this section, we're going to look at triggering from a digital events perspective. And in order to demonstrate that, I'm going to use SPI. Now, this is the serial peripheral interface. And many of you may not understand about SPI. So here's a very, very brief introduction to it. SPI is a master-slave type configuration where you have a clock generated by your master system, and data is both transmitted and received at the same time by the MISO and the MISI pin, which is the in and this is the out. Now, this display that we're going to use to demonstrate this only receives data. It doesn't actually return data, and that's why we've only got the MISO output. This is the chip select, and all SPI devices require a chip select to tell the device what the clock and the data is relevant to, which device you want to talk to. So you can actually network these, but each device on the network must have its own chip enable or chip select. So that's what's going on in here. So how do I go about demonstrating this? Oh, and just briefly, mode 0 is specified by the idle state of the clock and the way in which data is actually latched to actually either transmit the data when it's stable, or to actually shift data back out. And so in this case, on the rising edge of the clock, this is when you sample data, and on the falling edge of the clock, this is when data is shifted out. So that's a point at which data will change on your data bus. So that's just the definition of mode 0. Now, how are we going to demonstrate this? Well, what I've done is, let me just swap my camera over, and here you will see this may be familiar to you with some of the other videos. This is the sensor development platform as used by my MEC 2200 students at the University of Leeds. And here we have a microcontroller, which is actually the master unit to drive the SPI. Now, this port here is a general purpose output port for I2C or SPI devices. And normally this is the display that we're talking about, and this would normally plug straight into this port. However, in this case, I want to break out the wires so that I can actually look at this and demonstrate to you what happens and how to capture a protocol type signal. Okay, and this is what we're doing in this session. So the other important thing to note about this is that this microcontroller is also running an HMI, that's a human machine interface, and it allows us to interact with this from a terminal emulator. And here is the comms port to allow us to do that. And so what I'm going to do now is I'm going to swap my screen over and show you how the HMI works. So let me just swap this over, go to the terminal emulator, and here you will see the terminal emulator HMI. Now, this HMI, let me just split my screen so that you can see what's going on here. Right, so that HMI that you see here is being generated from this microcontroller, and it allows me to control when I send data out in the SPI to this display. So just to give you an idea of what's going on, I'm actually going to go to this HMI and I'm going to tell it to send data to the display. Now, just so that you're aware, if I go into the datasheet for the display, this is the command set for the display. So if I want to clear the display, I just send the command 76 out in hex to the display, and that will clear it. If I want to send data to the display, then what I can do is I can set the cursor position on the display. So this is what the 79 command does. And then I send another byte, which tells me, do I want to start with the leftmost digit, or do I want to start with the next digit, or the next one, etc. And so there are four digits in this display. Therefore, we can choose 0 through to 3. And then once I've sent that command, I can actually send the ASCII characters for the display. So I can go, for example, if I want to do 1, 2, 3, 4 on my display, I would send out 79 first. I'm going to start on the leftmost digit, so I send 0, and then I send the ASCII 1, 2, 3, 4 to my display. So that's roughly what's going on when I do this. So let's go back to our HMI, And so you can see this for real. In order to demonstrate that, I'm going to go to the test 23, which is my 7-segment display. And here I can actually now control my display. And I'm going to go to option number 2, and I'm going to type in 1, 2, 3, 4. And if you look at the display, which is in the window on the right-hand side, when I press enter here, you'll see on the display here, you'll see 1, 2, 3, 4 coming up. And equally, if I want to clear the display, I can type in number 1 in my HMI, and you'll now see the displays being cleared. So I just want you to know what's going on behind the scenes, and so this is sending out SPI commands on the bus. So how do we actually extract all of this information? So let's go to our PicoScope, and I'm just going to get rid of my split screen like that. So I'm going to set this up once again from a place of knowledge. Okay, so what do I know about my setup? Well, first of all, I'm going to look at channel A, and I'm using ×10 probes. So I'm going to set my probes to ×10. And on the vertical scale, remember, I'm working with digital signals that are going from 0 to 5 volts. And so if I set this to 5 ± 5, then I might go over range. So it's best to set to ±10. So I'm going to set that to ±10. And there's a DC coupling. Everything else is normal there. So I'm also going to channel B. I'm going to switch that on to manual. My probes are on ×10. And the vertical, once again, is going to be 0 to 10 volts, which is great. And let's see, what else do we need to set up? So once again, it's a DC coupling and no other settings on there. So that's great. Now my SPI is running with a clock of 125 kilohertz. So I'm going to set this to 10 microseconds, which is approximately the sort of time base I need to be looking at. And also I'm going to look at the trigger, which I'm now going to set this to normal. I could use single or normal, but because I've got control through my HMI, then I don't need to go to single shot, because it will only show me what it'll catch whatever I transmit under my key commands through my HMI. So I don't need to go to single, I can go to normal in this case, which is great. We're going to go to simple edge, which is fine. We're going to trigger on channel A, which is our clock source. And I'm going to leave the pre-trigger at 50, and I'm going to set my threshold because my digital signal is going from 2.5 volts. Well, at least the midpoint 2.5 volts, so that would be good. So I know it will capture it, and there you will see my trigger point. Now I'm going to separate out these waveforms because they're both based around the 0 volts line here. So my 2 channels, so I'm just going to raise this one up here, and I'm going to bring my channel B down to here so that I can separate out these signals and see them in a bit more detail. So I've now got this pretty much set up to go. So let's now go into the HMI, and I'm just going to use the simple command. Let me just show you what this is. I'm just going to send the clear display command, which is a single byte command, which is transmitting 76 in hex. So let me go to my HMI. I'm going to press number 1 to clear the display. And now let's go to my scope. Now, in the background, it's been capturing this, which is great. Now you'll see here that it's slightly overrun here because I've got, this is a byte transmission. So I've got 8 clock cycles to get the full 8 bits of my byte transmitted, but we've got 1, 2, 3, 4, 5, 6, and 7 there. So I haven't got it, and my time base is actually not quite right for seeing this data. So I've got 2 options. I can either change my time base and make it a little bit slower so I can catch more data in the time frame. Alternatively, I can change my pre-trigger because I'm not so interested in what's happening before here. So what I might do is change my pre-trigger, change it to 10%, and now you'll see it's shifted the waveform across. And now what I can do is rerun my HMI to get another scan. And I'm going to go 1 and enter, and now go back to my scope, and now you will see my SPI data. So I've got the full 8 bits, and so I can now analyze these in data. Now remember from my presentation here that on the rising edge, that's when I actually can look at the data and clock the data to find out what's going on. So let me go back to my scope. So on the rising edge, my data is valid. So if I look at this on the rising edge here, we've got a 0 data state at the moment. And if I go on this point here, it's a 1. This point here on the rising edge, it's a 1. This point here, rising edge, it's a 1. This point here is a 0. This point here, it's a 1. This point here, it's a 1. This point here, it's a 0. So that means that my data being transmitted is 0, 1, 1, 1, 0, 1, 1, 0. And that in hex is 76, which is the command that I've sent out. So it's looking good. That's great. But what about looking at a signal where I've actually got more data? So what I'm now going to do is, if I want to see more data, I've got to shut my time base down again. So let's have a look, go to my time base, and let me go to 100 microseconds per division. And now, because it needs to do a rescan, so I'm now going to issue the same command on my HMI. I'm going to clear the display and just show you that, there we go, it's redone a scan. It's picked up the start of my clock. And because I'm in control of the transmission, this is why in the from a trigger perspective, in normal mode is fine because I'm controlling when this data is issued. So I don't need to use single shot. So there we go. There's my clock signals, all 8 of them, and there's my data. So now let me send a different command out. So let me just go and look at this. So I'm going to send out the cursor control command, which is 79. I'm then going to say start from the leftmost digit, so it's going to then send out 0, and then I'm going to send out the numbers 1, 2, 3, 4, which is which are ASCII equivalents of the of those digits 1, 2, 3, 4. Okay, so it's going to go 79, 0, and then ASCII 1, 2, 3, 4. So let's go to my HMI, and I'm now going to go to option 2 here, which is the load numerical string from digit 1, which is left justified. So I'm going to go to 2, and then I'm going to go 1, 2, 3, 4. Now let me just split my screen so that you can see this, if I can find the split screen. So you'll see at the moment the display is clear, but as soon as I press enter here, you'll see those digits have now come up as 1, 2, 3, 4 on my display. And if I now go to my PicoScope, you will now clearly see that 5 digits have been transmitted. The first one, let's just go back here. The first digit that was transmitted will be 79, and the next one will be 0. So let's have a look at that. So here we go. There's the first digit here, and that's the 79. The second digit here is 0. All my data bits are 0. And the rest are the ASCII characters 1, 2, 3, and 4, which you can see here. Now, I'm not going into detail about expanding this and analyzing this because this is not about triggering. This is about that's about zooming in and doing other things, and that really is a separate video. But this is about how to set up triggering so you can actually get and capture what you want to see. Okay, so what would also be interesting to see is the what's going on. Oh, let me just get rid of my split screen here because I keep on forgetting to turn that off. There we go. Right. So what would be interesting to also now see is where's the chip enable in all of this. So what I'm going to do is I'm going to just go back to my circuit, and rather than looking on channel 2, which is this channel here, looking at the data output, I'm going to change this to the chip enable, and I'm just going to push that into there. And I'm now going to go back to my PicoScope. I'm now going to go back to the HMI, and I'm going to now reissue what I just did. So I can change the characters. Let me just split my screen so you can see this. There we go. So what I can now do is go into option number 2, and I can go 5, 6, 7, and 8, and then press enter. You'll see now that 5, 6, 7, 8 has come up on my display. But what I'm interested now is in what the chip enable's been doing. So I'm just going back to my screen here and also going to the PicoScope, and it hasn't picked it up. Let I don't quite know why it hasn't been that. That could be because I'm trying to do screen capture and stuff at the same time. Let me just go back into my HMI. It's live television, folks. Let's go to 2 and 5, 6, 7, and 8 and enter. And let's go. There we go. Yay. It caught it this time. So now you'll see this is the chip enable. And if I bring the chip enable up, or just bring these two signals closer together, you can see that in accordance to the SPI protocol, the chip enable has to drop first before the clock data comes out. And when all the data has been transmitted, you can raise the chip enable. And here in my scope, you can see exactly that. You can see the chip enable has gone down. There's my 5 bytes that have been transmitted. And then when it's complete, the chip enable has gone back up again. And if I had a 3 or 4 channel scope, then I would be using this chip enable as really my primary trigger, so I can look at everything relative to that edge. But because I've only got a 2 channel scope, I have to decide what's the most important thing in this case. And so this is where you can actually select your sources, either source A or source B, in this case, to decide where your priorities lie and what you want to see. So I hope that's actually made sense and you've seen it from a digital perspective. And let's go back to the presentation. So in this final bit, we're going to look at switch bounce analysis. And this is really interesting from a scope triggering perspective. Okay,